Welcome back to our next segment. This will be about digital signatures based on the discrete logarithm problem. And we will actually take a little detour to construct these schemes. And this is because the popular ones, so the ones that are really used in practice, they're all based on a very specific construction that turns an identification scheme into a digital signature scheme. And without having seen this, they just look a little bit weird and a little bit awkward. So I want to take the time to make this little detour with you and to initially look at what is called identification schemes. Now, in principle, this is not really anything new because we have looked at key distribution in our journey from symmetric key cryptography to public key cryptography. And we looked at a number of schemes for the distribution of symmetric keys. We also looked a little bit at schemes where we sort of use already public key methods to distribute secret keys. And it doesn't really matter whether we talk about symmetric or public key cryptography. An essential component of these kind of schemes was that of perhaps implicit entity authentication. So for the schemes that we considered, we realized it would be really important to know that we are exchanging a key or transferring a key to a specific other party, so a party that is in possession of a very specific other secret key. And this is what identification or entity authentication is all about. We want to establish contact with a party, and not just any old party, but the party that has access to or is in possession of a specific secret key. And it's the secret key that we have the public key for, basically. So the way in which these authentication protocols normally work is that some form of challenge and response has to be done. And this is because we want to avoid replay attacks or reflection attacks. So attacks where essentially we take old values from previous protocol runs and replay them or reflect them back to a party and thereby fool them into something. And in particular, in the context of an identification scheme or entity authentication scheme, so these kind of two words are used by cryptographers pretty much interchangeably. What we want to ensure is an adversary cannot fool a party into believing that they are a different party. So often we just use the abbreviations A and B in these games. In the context of identification schemes, it has become kind of folklore really to use P and V as the abbreviations for the parties. So P is the prover and V is the verifier. So schemes that we have seen before, they can have a different number of rounds, typically 2 or 3 to achieve really entity authentication. And the kind of entity authentication scheme that is useful to then kind of come to a digital signature scheme would be a 3-round identification scheme. So on the right-hand side here, I have got the kind of prototype of such a 3-round scheme. So this is what we will base then also our digital signature schemes on. So there are 3 rounds where messages are being exchanged between the prover and the verifier. So the verifier knows about the prover, trusts their public key. The prover then initiates the protocol by sending a message I to the verifier. So here we've got prover, and they send a message I to the verifier, whereby this message I is derived by running a function P1 on their secret key. So this will deliver a message I and some form of state information that will be useful later on. The verifier then, in this kind of abstract definition of the protocol, will then respond to the prover with a random value, and this is basically their challenge. And here again, the symbol that I'm using here, this means draw at random from some well-defined distribution. And the prover then responds with S, with their response value then. And this is essentially calculated with another algorithm, P2, which takes again their secret key, the previous state information, and then the R. So the state information could just be the I, the initial commitment, or it could be something related to it. And in the end, the verifier can verify that the protocol has run successfully, so that P is really who they claim to be, by running some verification function V using the public key and the R and the S that have been exchanged, and this should match somehow the I. I realize this is really abstract, and I do this kind of deliberately because we will in a moment then put a real entity authentication protocol into this abstract description, and then we will transform this into a real digital signature scheme. But it's, I think, really useful to have the kind of the template of such a 3-round authentication scheme written down in this more abstract way. So this kind of protocol construction is what we are working with. And then there's a very famous transform, which is called the Fiat-Shamir transform. And this essentially collapses this 3-round interactive authentication scheme into a non-interactive signature scheme. And it's perhaps really not very surprising of how you do that. So the Fiat-Shamir transform works as follows. So it defines essentially a signature scheme based on such a 3-round authentication scheme. You generate a key pair in the usual manner, whatever your trapdoor function is. You then essentially sign a message by doing the entire 3-round protocol that is sort of an interactive thing between prover and verifier. All of this the signer will do in a completely non-interactive manner. So they will produce the first message that the prover will produce. This is the one here. Then they will kind of emulate the verifier by spitting out a value R, that is the hash function, that is a hash function value applied to I and M somehow. So this is again still a bit abstract. And then they will produce an S by using the P2 from the interactive protocol and apply this to the secret key, the state, and R. And then essentially everyone can be the verifier later on by checking with a sort of a verification function that the I that they can crank out from that is then satisfies the condition that R equals H of I and M. So I know this is abstract again, but this is sort of the template that we will be applying to the more concrete scheme that I will show you in a moment. And the cool thing about this transform is that no matter which 3-round identification scheme you take, assuming though it fulfills some specific security notions around these kind of entity authentication protocols, then with this kind of transform, you can transform it into a secure signature scheme. So a signature scheme that satisfies the EUF CMA security notion. And this is pretty cool, really. So one of the important things here is, again, which we kind of don't really go to close, is that this works because in the security proof we make a very crucial assumption, and this is that we model H as a random oracle. And I've used this a number of times. If this is still slightly alien to you, then perhaps just go back and see where we introduced this idea, and also perhaps if you haven't done so, read a little bit up on it, because it is then sort of an interesting kind of concept that we are using in a proof. In practice, we just translate it into a secure hash function. Now, you could sort of wonder, does this Fiat-Shamir transform really securely bind the values R and S, which eventually constitute the signature to a message? And if we sort of go back and have a look, then what you'll see here, the R depends on the M. So it's bound to it via hash function. And then the S, because it depends on the R, ultimately also is kind of tied to the value of M. So a different M will produce a different R and a different S. And this means that kind of intuitively, there's really a strong binding between message and the resulting signature. So let's apply this to a well-known identification scheme. And I'm using this particular one because it's really quite popular in a variety of applications. In particular, also, if you think about the case where you have a small embedded device that you use as part of an authentication program or process, like, for instance, your bank card. When you authenticate yourself to the ATM machine, so the cash machine, then you kind of do a two-factor authentication scheme here. You present the card, so you've got possession of something, and then you present also the knowledge of the PIN, so you know something. So you've got two different factors. And the card, in fact, also authenticates itself in that process. And there are different types of authentication schemes that cards can use, and one of them would be this Schnorr identification scheme. So it's based on the hardness of the discrete logarithm problem over ZQ. So the field of integers modulo the prime number q. Key generation works in the usual sort of way that we have seen for discrete logarithm based systems. So we draw a secret key x at random from ZQ, and then we compute the public key y by just raising g, the generator of the group, to the power x. And so all of that here works in ZQ, which means that I'm using here really sloppy notation. I've warned you about this before. In many cases I'm not using sloppy notation, but here it kind of looks weird if you use decent notation. So in principle, when we are computing y, which is g to the x, then we are doing this mod q, which means that this here is not an equal, it's actually an equivalent sign. And equally here, all of these things become equivalent signs, and I've just optimized them away. So everything here, this whole world, is done modulo q. Okay? So the process here is actually quite simple. So we generate a private key, there is a secret key, there's also a public key as usual, and then the prover initiates the protocol by randomly sampling a number k, and then by producing an initial commitment, which is simply g raised to the power k. So we have seen this kind of way of working over and over again in the case of discrete logarithm-based systems. So this I is sent over to the verifier. They in turn choose a number r, which is again randomly chosen from ZQ. And the prover then computes s equals r times x plus k. And sends the s over to the verifier, and the verifier can now verify. If all has gone well, then I should be equal to g to the s times y to the minus r. And if this is the case, then they will accept the prover as really the owner of the secret key x. So perhaps the first thing to do is to convince ourselves that this scheme is really correct, meaning that a valid run of the protocol means that the verifier will indeed accept the prover P's commitment. And I would suggest perhaps you pause the video here and try and do this little verification routine yourself, and then only check sort of the solution in a moment. Okay, so let's have a look at this. In the verification, we are checking the term g to the s times y to the minus r. And we will simply do that by plugging in the definition of s and of y. So we have g to the s, and s is given here by the protocol run. We assume everything has been all right. So we just plug in r times x plus k. And then we have got y to the minus r. So y is the public key, and that is also g to the x. So we have now g to the x and to the minus r. And now you can see that we have got here a term, g to the minus xr. And there is also a term, a partial term, which is g to the plus xr. So these will just cancel each other out. So this will then hence give us just g to the k as a result. Now, what is g to the k? Well, per definition here, that's actually our initial commitment I. So what we can see is that for a faithful protocol run, if we compute g to the s times y to the minus r, we should indeed get an expression that is equal to I, the initial commitment of the prover. Now, in terms of security, what can we say there? Well, now let's suppose we just look at a passive adversary at first. So a passive adversary can't really get involved in a protocol run, but they can observe all of the values that are being exchanged. Now the question is, could a passive adversary pretend to a verifier that they are actually an honest prover? Now there's an interesting argument that I'm going to use now. So, and this is sort of intuitively taking advantage of this kind of notion of not revealing any information means that there is no information about the secret in a protocol run. And so how could I argue that there is no information about the secret key in the protocol run? Well, I could argue that if I was able to create a valid protocol run without knowledge of the secret key. So how could I do that? Well, it's actually really quite easy here. So all what an adversary would need to do, or all what we need to do in a way, is we can pick two random values, R and S, in ZQ. And then it's always possible to claim to produce a valid I by taking G and raising it to the power S. And I'm sorry for the typo here. And then by taking Y and raising it to the power minus R. And if I'm doing that, I can produce a valid I, obviously, because this is my verification condition, which means that in a way everybody can produce such a correct protocol. So it's possible to have an I and an R and an S that fit exactly the specification of the protocol. And this can be done without any knowledge of the secret key, which implies that this kind of triplet has got no information about the secret key in it. And from that we can conclude that purely passive attacks can't work. It's also possible to reason about active adversaries, but that again goes beyond what we can actually achieve here in our undergraduate course. And so what I want instead is to just now show you how this identification protocol gets mapped to a signature scheme. And you map it really by using the Fiat-Shamir transform. And that then results in this following Schnorr signature scheme. So you have got the usual secret and public key generation, and you also define a function h which maps an arbitrary bit string into an element of ZQ. And then your signature generation is really easy. You essentially generate a random k, like you would do in the identification protocol. You set I equals g to the k, like you do in the identification protocol. Then you compute an R, which is h of I, and you now simply append the message m. And then S equals R times x plus k. As you would expect, it's exactly from the identification protocol. And the signature is R and S. So we've just followed the Fiat-Shamir transform step by step. And then when you verify, we do again exactly what Fiat-Shamir suggests. We essentially compute an I by a verification condition, and then we accept the signature if R equals h of I appended to m. And again, you could pause now and actually check that this signature verification will accept valid signatures with really high probability. It's as straightforward as the computation that we have done before. So that's one really popular signature scheme based on discrete logarithms. The second one is part of a standard, of the digital signature standard, DSS. And the signature scheme in it is called DSA, and its elliptic curve variant is called Easy DSA. And they really, both of them follow exactly the same template. So I was also tempted to just describe both of them using some unified notation, even though we haven't really touched elliptic curves. It doesn't really matter. One of the reasons why I'm including elliptic curves here is because in practice and in many practical applications, you would actually see that elliptic curves are being used these days. And this is although they are now also becoming deprecated again. So this is one of the, I would say, very interesting stories in cryptography, that already in the 1980s, it was quite clear that elliptic curve groups would offer a much better security performance trade-off, because in these groups, the discrete logarithm problem is much harder. And this means that we can choose shorter keys and still have a better security margin than when we just work over prime order subgroups. But the issue is that with now, I would say, the much more serious emergence of quantum computing and the ability of doing certain algorithms on a quantum computer really much more efficient than on a classical computer, the fact that elliptic curves have fairly short key lengths make them also more vulnerable to this emergence of quantum computing. And even though most experts believe that quantum computing is probably 30 or 50 years away from being an actual threat to cryptography, NIST has decided that it's time to already start transitioning away again from it. And this is not just a weird kind of quirk of NIST. If you consider what we have seen before in the context of symmetric encryption, we have seen that DES, the data encryption standard, is really a very, very old standard, and it was sort of rescued by the triple DES way of working with DES. And AES has come in the meantime, and many other algorithms have come in the meantime, and still our banking system still relies on triple DES. So transitioning away from a specific standard in cryptography is a process that takes decades. Hence, perhaps the move of NIST is not as weird and awkward as it looks. So DSA is then based on another discrete logarithm-based identification scheme. And as before, I've written it down so you can see how to get from the identification protocol to the signature scheme. So it's really, really similar. So like in the Schnorr scheme, we choose initially a random k in ZQ, and then we compute our initial commitment I equals g to the k. All of the operations here are again done modulo q, so I use sloppy notation. The verifier, now in contrast to before, they not just choose a single random value r, they also choose a value alpha and send this over to the prover. The prover then computes a slightly more complex, perhaps, equation than before. So S now is equal to k inverse times alpha plus x times r. And then the verification, first of all, checks whether S is equal to 0 or not. It shouldn't be. And if this is the case, then you also check if I equals to g to the alpha times S inverse times y to the r times S inverse. So you can see it's really, really similar to before. It's just slightly more complex in terms of the exponents. And as before, the security relies on the discrete logarithm problem, and we'll just believe that. Now we can again apply the Fiat-Shamir transform. This time it's slightly adapted in the sense that because there's an alpha, we set the alpha to be equal to the hash value of m, and the r is just f applied to I, whereby f is a function that maps from one group G to ZQ. And that's kind of handy because for just the standard DSA, f of I doesn't really do anything because I is an element mod Q anyway per se. And so it just retains this structure in the case of a different group perhaps sitting underneath where the actual secret key and public key live in. So in the case of ECDSA, where this would be an elliptic curve group, we have a slightly modified version of f. So elliptic curves are just equations defined over a finite field. And the equations are in a two-dimensional space. So you've got so-called elliptic curve points. They've got an x and a y coordinate. And the way in which we work here with such a point in DSA is that we simply say our transform f just takes the x coordinate of whatever the elliptic curve point is. So the digital signature algorithm is then defined as follows. Generate a secret key and a public key, whatever your underlying group is. And then when you assign a message, we take the secret key, we take the message, we now sample a uniform k, and we compute our sort of commitment, which is g to the k. And then we compute an we compute an r, which now is either just g to the k, or it's just the x coordinate of the elliptic curve point that results from the analogous operation. And then s can just proceed as before. So there's a bracket missing here. So that's k inverse times h of m plus x times r. If either of the resulting values r or s are 0, then we just have to try another k and see what r and s is. Once we have found an r and s which is non-zero, then we have got a valid signature. And verification, we kind of have the similar expression as before. We just compute g to the s times y to the minus r, and we accept a signature if we have to check a slightly more complex equation here. And again, like before, I would encourage you to actually check for yourself that if a signature is valid, then this is the verification here will succeed with really high probability. So this brings us to the end of the digital signatures part of the course. As usual, there are also some hands-on exercises, which, as you know, you can do in your own time.